Hello guys, so welcome to our VHDL lessons. In today's lesson, we're gonna explore the first two or simplest multiplexers ever, which is basically the 2x1 multiplexer or mux and the 4x1 mux. So they are, really easy ones. So I'm gonna, use the statement with select when to represent them with as a truth table, which is really very easy and very convenient. So let's start by the mux 2x1. So in this one here, I implemented it using this, enable input, but it's an inverted enable, because in the book there are some examples that use inverted enable inputs. That's why I just choose to do it in that way. Okay. Remember, inverted enable means when enable is 0, it's enabled. When enable is 1, it's disabled. Okay, and the output should be 0. Okay. So the truth table is really easy. When the selection is 0, y will be equal to I naught. I mean I0, the first input. When the selection is 1, y will be I1. Okay. Provided that the enable at the time is 0. So the circuit is enabled. Otherwise, y will be equal to 0 all the time, regardless of the S or the I naught or the I1. So here's the design. It's really a very simple one. Okay. We have two inputs, I0 and I1. Selection is 1 bit as well. The enable bit, and then the output is also 1 bit. Okay. Since we need the enable to know if the circuit is enabled, so it will function as a multiplexer or disabled, so it will just give 0. So I made this signal here called SE. SE basically means it's a signal that combines basically the both E and S at the same time. Okay, S and E basically. So it's basically the concatenation of S and E. Okay, now y the value of y will be determined based on that concatenated signal SE, which basically gathers the input S selection and the input enable or the enable bit. So when the circuit is enabled, means E, which is the second bit, is 0, and the first bit S is 0 as well, then Y will be I0 or I naught. If the circuit is enabled and the selection is 1, then Y will be equal to I1. Otherwise, Y will be 0. Otherwise means when E is 1, whatever S, whatever I naught, whatever I want. Okay, that's a really very simple one. Now let's check the 4x1 mux. I implemented it without using the invert, just to show you both at the same time. So a good thing here to implement that 4x1 mux is to combine all the 4 inputs in one input, but 4 bits. So you have here an input called I. I is 4 bits, 3 down to 0. Okay. And the selection as well is also, instead of having 2 inputs called S0 and S1, I will make them just one input called S, and S is 2 bits, 1 down to 0. And in any case, the output is Y or F. I called it here F, that's fine. Okay. It's just 1 bit. Good. Now, here is the truth table. It's a really easy one. So 0, 0, Y will be I0, 0, 1, I1, 1, 0, I2, 1, 1, I3. So with this, I'm going to select the value for F based on S, and there is no enable here. F will be I of 0 or I naught when S is 0, 0. It will be equal to I1 when S is 0, 1. And remember, S is 2 bits. It will be equal to I2 or I of 2 when S is 1, 0. Otherwise, which is basically the last case, which it will be 1, 1. Okay. Now I'm gonna test just one of the design. I'm gonna test the 4x1. Of course, the 2x1 is really easy. Okay. So here is a 4x1 mux. So let's compile. Good. So just to give you a highlight about the, so we're gonna test the circuit based on the inputs. The inputs are S, which is 2 bits. So it's changing from 0 to 3, 0, 0, 0, 1, 1, 0, 1, 1, which is 3. And the second input, which is I, which is 4-bit. 4 bits means I'm gonna change from 0 to 15, 16 cases. So here is, the counter for the I input from 0 to 15. Okay, so let's simulate that. Start simulation. So let's get what? The max. Max 4x1 test bench. Really easy one. Just 3 variables, 3 signals. So here is based on the selection we're going to choose. Okay. And it's good to, to expand. Let's also do radix here for this one. So how many cases we need? We need basically 64. How? Because S is changing from 0 to 3. So 0, 1, 2, 3. And for each count of S, I will change from 0 to 15. So we need 16 by 4, it is, or times 4, it's 64. So let's make it 80. So let's run for 80. So let's run this. Let's change S is radix is good. And let's now check it out. So basically, this is I0, I1, I2, I3. So when S is 0, we always take this bit here. So look, this bit is going, up and it's rebelling all the time. 0, 1, 0, 1, 0, 1. So look at F. 0, 1, 0, 1, 0, 1, and so on. Until we change here because S now become 1. So we're gonna take this bit in here, which is changing by every 2 cycles, we can say. So look, F is changing every 2 cycles. So 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, then 1, 1, 1, 1, and so on until we reach 2. S is 2, so basically we're gonna take I of 2 or I2, which is changing each 4 cycles. Look now at F, 4 cycles and the change. It's following, so this signal here, the last one, is following basically this signal with the changing, each 4 cycles. And this will continue until we reach 3. And finally, this bit here is changing each 8 cycles. Look, 0 for 8 cycles, 0 for 8 cycles, then 1 for 8 cycle, 1 for 8 cycle. Okay, guys, that's it for the multiplex. Of course, the 2x1 will be much easier than this. Okay, so thank you very much for watching this video and see you in the next lesson. Bye-bye.